Okay, imagine tackling problems so complex they'd take today's best computers, well, thousands of years to solve. Now, picture solving those same problems in just minutes. Sounds like science fiction, right? Welcome to the deep dive.
Today, we're jumping into the really fascinating, sometimes baffling world of quantum computing. Our goal here is simple. Unpack what it is, how it works based on those mind-bending quantum principles, and crucially, what it means for the real world. We want to cut through the hype and give you the core insights. And to help us do that, we're drawing on some excellent material from IBM, specifically their What is Quantum Computing Guide. It gives a great foundation.
It really does. So quantum computing, it's basically a whole new approach using the rules of quantum mechanics, the physics of the very small, to build and operate computers. And the reason that's exciting is the potential speed. For certain types of problems, these machines could be unbelievably faster than anything we have now. We're talking, potentially turning millennia of classical computation into just hours or minutes. It leverages quantum physics directly. That kind of leap is hard to even grasp. Is this still mostly theoretical, stuff happening in labs, or is it closer than we might think?
Oh, it's definitely moved beyond just theory. You've got major players, IBM obviously, but also Amazon, Microsoft, Google investing heavily, plus tons of startups. And it's not some small niche anymore. Some projections see it hitting, get this, like a $1.3 trillion industry by 2035. So the momentum is real.
Wow, 1.3 trillion, that's huge. But what could stop it? I mean, what are the big roadblocks to hitting that kind of number? Are there major pitfalls?
That's a really important question. Yeah, there are definitely challenges. Scaling up the hardware is tough.
Yeah.
Making these quantum states stable, keeping them from getting disrupted is incredibly hard. And then finding the best algorithms, the killer apps that really show off the power. That's ongoing work too. We're still early, but things are moving fast. Overcoming those hurdles is key to unlocking that potential you mentioned.
Okay, so it's powerful, it's developing fast, but let's bring it down to earth a bit. What kinds of actual problems, things that affect us, could this technology solve? What's the so what?
Right. Broadly speaking, there are two main areas where people expect quantum computers to really shine. First, simulating physical systems. Quantum mechanics basically is the operating system for reality at the smallest scales. So a computer built using those same principles, it's naturally good at modeling molecules, materials, that kind of thing. Think about drug discovery. Right now it takes ages, costs billions. A quantum computer could potentially model how drug molecules interact much faster, maybe cutting that down to months. Or designing new materials for batteries, catalysts.
Okay. So using quantum to understand quantum, that makes sense.
Exactly. The second big area is finding patterns in data. Quantum computers have mathematical tricks up their sleeve, things classical computers just can't do. They can look at huge, messy data sets and find structure, find correlations that we'd otherwise miss. This could be huge for things like, say, protein folding in biology, understanding diseases, or even complex financial modeling.
It definitely feels like we need to shift our thinking to get this. You mentioned the quantum realm is bizarre, counterintuitive. That's putting it mildly, right? Things just don't work the way we expect down there. And instead of the usual zeros and ones, the bits, we have these qubits.
Precisely. And these qubits operate under quantum rules, which gives quantum computers their power. These rules allow access to completely different mathematical approaches. There are four main concepts you really need to get a handle on: superposition, entanglement, interference, and this thing called decoherence.
Okay, let's break this down. Superposition first.
Right. So a normal bit is either 0 or 1. Simple. A qubit, though, thanks to superposition, can be a 0, a 1, or crucially, a combination of both at the same time. It's like it exists in a fuzzy state between the two. And when you link qubits together, this property lets you represent a massive number of possibilities simultaneously in this kind of complex, multidimensional space. But here's the catch. The moment you try to look at it to measure it, that fuzziness collapses and you just get a plain old 0 or 1.
Okay, fuzzy state collapses on measurement. Got it. What about entanglement? That always sounds a bit spooky.
Yeah, Einstein called it spooky action at a distance. It's the ability of qubits to have their states linked, fundamentally correlated, no matter how far apart they are. What's really wild is if you measure one entangled qubit, you instantly know the state of the other one or ones it's linked to. They act like a single system, even if they're miles apart. It's a deep connection.
Okay, still sounds spooky, but I think I follow. Next up was interference.
Interference, yeah. This is really the powerhouse, the engine of the computation. Because qubits in superposition behave a bit like waves. They have amplitudes, kind of like probabilities, for different outcomes. And just like water waves, these probability waves can interfere. They can add up, making certain outcomes more likely. That's constructive interference. or they can cancel each other out, making other outcomes less likely destructive interference. Quantum algorithms are designed to carefully orchestrate this interference to boost the probability of the right answer and cancel out the wrong ones.
So you're basically using waves to find the signal in the noise.
That's a great way to put it. And finally, there's decoherence. This is essentially the enemy. It's when the quantum system loses its quantumness, its superposition and entanglement, usually because of interaction with the outside environment like tiny vibrations or stray heat. It collapses the state back into a classical one, destroying the computation. Measurement is a form of controlled decoherence, but you want to avoid the uncontrolled kind at all costs.
That sounds incredibly difficult then, trying to keep these states perfectly isolated. What does that actually involve? Like physically? Are these things kept in extreme conditions?
Oh, absolutely. That's one of the massive engineering challenges. Often the quantum chips need to be cooled down to temperatures colder than deep space, just fractions of a degree above absolute zero. They need intense shielding from magnetic fields, from vibrations, from basically any environmental noise. You're trying to protect these incredibly fragile states.
Wow. Okay, so how do those four principles, superposition, entanglement, interference, avoiding decoherence, actually work together to compute something?
Right, so a typical quantum computation goes something like this. First, you prepare your qubits in a specific initial state, often putting them into a superposition representing all possible inputs or states. Then you run a sequence of operations, called a quantum circuit, which is programmed by your quantum algorithm. These operations use things like precisely timed microwave pulses to manipulate the qubits, entangle them in specific ways, and control that interference process. The interference pattern evolves, canceling out the paths leading to wrong answers and amplifying the paths leading to the right ones. Finally, you measure the qubits. Because of the interference, you're now highly likely to measure the state corresponding to the correct solution.
It's like guiding possibilities towards the right answer instead of checking every single one. The qubits seem central to all this. We know they replace bits, but what are they physically, and how do they get that exponential power?
Physically, they can be different things, as we'll touch on. But the core idea is they hold that superposition state 0, 1, or both. The real power comes from scaling. Two qubits can hold 4 states at once. 0, 0, 0, 1, 10, 11. 3 qubits hold 8 states. It doubles each time. By the time you get to, say, 100 qubits, the number of states they can represent simultaneously is astronomical. Literally more possibilities than atoms in the universe. That's the exponential advantage.
Okay, that scale is mind-boggling. You used a maze analogy earlier. Can we revisit that? How does a quantum computer navigate it differently?
Right, the maze. So a classical computer might try every path one by one, brute force, go left, dead end, go back, keep going until it finds the exit. A quantum computer, using superposition and interference, doesn't really walk the paths in the same way. It's more like it gets a probabilistic overview. The interference cancels out the likelihood of being on paths that lead to dead ends and boosts the likelihood of being on the path to the exit. So when you measure, you're overwhelmingly likely to find yourself on the correct path out. It's not checking faster. It's using quantum effects to essentially filter possibilities far more efficiently.
So it's not really knowing the path beforehand, but more like the wrong paths just fade away due to physics.
That's a good way to think about it, yeah. The algorithm is designed to make the wrong solutions interfere destructively, essentially canceling themselves out, while the right solution interferes constructively and stands out. It's elegant, really.
And physically, what forms do these qubits take? Are they all the same?
No, there are several different approaches being developed, each with pros and cons. Superconducting qubits are very common, used by IBM and Google. They're fast, but need those ultra-cold temperatures. Trapped ions use individual charged atoms held by lasers. They're very stable, high fidelity, but generally slower to operate. Then you have quantum dots, tiny semiconductor crystals acting like artificial atoms, and photonic qubits using single particles of light, which are great for communication. Each has potential for different applications or parts of a system.
Okay, so the chip itself might be small, but you mentioned the cooling. When we see pictures, they often look like these huge, complex, chandelier-like structures inside big cylinders. What are we actually seeing there?
Yeah, those elaborate structures are usually the dilution refrigerators needed to get things incredibly cold.
Yeah.
The quantum chip itself is tiny, often at the very bottom. So the main physical parts are the quantum processor itself, with the qubits, then the cryogenic system of the refrigerator keeping your absolute zero and prevent decoherence, using superconductors and specialized materials.
Yeah.
You also need sophisticated control electronics, often at room temperature, sending microwave signals down wires to manipulate the qubits. And, crucially, the quantum software. That's becoming hugely important. Tools like IBM's Qiskit are vital. It's an open source toolkit lots of people use, over 500,000 users apparently at hundreds of universities. It lets people actually program and run things on these machines, and now they're even adding AI to help write quantum code.
That software piece is key. Which brings up a really common question. Is this technology going to replace my laptop? Is classical computing going away?
That's a big one. And the short answer is almost certainly no, not for most things. Think of it like this. Classical computers are your versatile Swiss Army knife. They do lots of things pretty well. Email, spreadsheets, games. They work sequentially with definite zeros and ones. Quantum computers are more like specialized heavy-duty industrial tools. They use qubits, superposition, interference. They're designed for very specific, incredibly hard problems that classical computers choke on. They don't even do math in the same way.
And the results are different too, right? You mentioned probabilities.
Exactly. Classical computers usually give you the answer. Quantum computers, because they're based on probabilities and measurement collapses the state, often give you a distribution of possible answers, or tell you the most likely ones. For the types of problems they tackle, like finding the best molecular configuration out of billions, getting the top few most probable answers very quickly, is vastly more useful than waiting centuries for a classical computer to find the single best one. It narrows the search space dramatically.
Okay, so they're specialists. When do we actually need one? Where's the line where a classical computer just isn't enough?
Well, for most everyday tasks, classical is fine, even better. You need quantum when you hit problems with truly massive complexity, tons of interacting variables, simulating molecules accurately, as we said, understanding exactly how every electron behaves, discovering new fundamental physics, maybe certain types of optimization problems with just vast numbers of possibilities. A classical computer might sort a database of known molecules, but simulating a new one from scratch. That's where quantum shines, because it can kind of mimic the quantum system directly rather than just crunching numbers about it.
So it's less a replacement, more a partner?
Absolutely. The future, at least for the foreseeable future, looks like hybrid systems. Classical computers will manage the overall workflow, handle input-output, and offload the really hard quantum bits to the quantum processor. They'll work together.
Makes sense. Now, IBM talks about stages of progress, quantum utility, and quantum advantage. Can you clarify what those mean?
Sure. Quantum utility is basically the point where a quantum computer can reliably solve a problem that's practically impossible for even the best classical supercomputers using exact methods or brute force. It's scientifically interesting pushing boundaries. IBM actually demonstrated this in 2023, which was a big step. Quantum advantage is the next, much bigger goal. That's when a quantum computer can solve a commercially or scientifically relevant problem better, faster, or cheaper than any known classical method, even clever approximations. It delivers real practical value. IBM is aiming for demonstrating initial advantage around late 2026, especially through that close collaboration between quantum and classical supercomputing.
So utility is it can do something unique. Advantage is it can do something useful better than anything else. How do we track getting there? Are there metrics?
Yes, measurement is key. IBM uses a few benchmarks. Layer fidelity checks how accurately the whole processor runs quantum circuits, giving a sense of component quality. CLOPS, circuit layer operations per second, measures the speed, how quickly it can execute standard benchmark circuits. It's like a measure of the processor's clock speed, but for quantum circuits. And circuit depth tells you how many steps or layers of operations you can run before decoherence messes things up. Deeper circuits mean you can tackle more complex problems. These help compare progress across different systems and time.
Okay, so looking ahead, what are the really big hurdles researchers are focused on right now to push past utility towards widespread advantage?
There are definitely some major mountains to climb. Number one is scaling the processors, getting more high-quality interconnected qubits. IBM has roadmaps aiming for hundreds, then thousands of reliable qubits. Number two is scaling the hardware system around it, making those huge fridges smaller, cheaper, more energy efficient. Three is absolutely critical, quantum error correction. Because decoherence is unavoidable, you need ways to detect and fix errors. IBM had a big breakthrough here recently, finding a much more efficient error-correcting code, which is vital for running long, complex calculations reliably.
Error correction sounds fundamental.
It really is. Then number four is finding more quantum algorithms that actually deliver that speed up on useful problems. Five is continually improving the software and middleware, like Qiskit, to make programming these things easier and more powerful. And six is building that quantum-centric supercomputing infrastructure, seamlessly integrating quantum and classical.
And assuming progress continues on those fronts, where do we see the impact first?
Well, the areas we touched on earlier look most promising initially. Pharmaceuticals speeding up, finding new drugs, chemistry and materials, science designing better catalysts, maybe for capturing carbon or creating materials with novel properties, and potentially machine learning using quantum techniques to accelerate certain complex AI tasks or handle data in new ways. The impact could be really broad eventually.
It's been quite a journey today, hasn't it? From the very basics through the quantum weirdness to the hardware, the software, and what this might all mean. It's complex, but the potential feels enormous.
It really does. We're seeing this transition from pure science fiction to tangible engineering and early applications. It's an exciting time.
So wrapping this up, maybe here's something to think about. We've seen how understanding the rules of the incredibly small, the quantum world, is letting us build tools to potentially solve some of the biggest problems we face. It makes you wonder, doesn't it? What questions, maybe ones we can't even conceive of yet, will become answerable when our computational limits are set not by classical silicon, but by the fundamental quantum nature of reality itself.